be the result of gravitational effects that cause matter to clump into filaments and clusters, leaving behind regions of relative emptiness. Despite its enormous size, the Boötes void is not completely empty. A small number of galaxies have been identified within it, but their distribution is highly sparse. The void's discovery initially raised questions about whether such large-scale structures could challenge existing cosmological models. However, further studies confirmed that voids of this magnitude are statistically plausible in a universe governed by the principles of structure formation through gravitational interactions. One of the most intriguing aspects of the Boötes void is its impact on the understanding of cosmic evolution. Large voids like this one offer insights into the processes that shape the distribution of matter on the grandest scales. They also provide a natural laboratory for studying dark energy, the mysterious force driving the accelerated expansion of the universe. Since voids are less dense than their surroundings, they exhibit weaker gravitational influences, making them valuable testing grounds for alternative theories of gravity in cosmological dynamics. The study of voids has advanced significantly with the advent of large-scale galaxy surveys, such as the Sloan Digital Sky Survey (SDSS), which have mapped the distribution of galaxies across vast cosmic distances. These surveys have revealed that voids are not simply empty spaces but contain a diffuse population of galaxies, intergalactic gas, and possibly exotic forms of matter. Some researchers have proposed that voids may even enhance our understanding of neutrino physics, as the low-density environments could amplify subtle effects related to neutrino interactions with dark matter and cosmic structures. Furthermore, the Boötes void serves as a reminder of the universe's inhomogeneous nature, where galaxies are not evenly distributed but are instead arranged in a vast cosmic web. This web consists of high-density filaments and nodes, separated by voids that vary in size and shape. The discovery of such structures has led to refinements in numerical simulations of the universe, allowing astrophysicists to test predictions about galaxy formation, dark matter distribution, and cosmic expansion. Some theories suggest that the Boötes void may be the result of multiple smaller voids merging over time, creating an exceptionally large underdense region. This hypothesis is supported by the presence of a few isolated galaxies within the void, which may have formed in residual filaments that failed to collapse into larger structures. These galaxies offer a rare opportunity to study star formation and galactic evolution in an environment relatively free from external gravitational influences. In addition to its scientific significance, the Boötes void has also captured the imagination of the public, inspiring speculation about whether such vast emptiness could be indicative of unknown cosmic phenomena. While some have suggested that large voids might be associated with exotic physics, such as modifications to general relativity or even artificial megastructures built by advanced civilizations, mainstream astrophysical research attributes their existence to well-understood processes of cosmic evolution. As observations of the large-scale universe continue to improve with next-generation telescopes and advanced computational modeling, voids like the Boötes void will remain essential to refining our understanding of cosmology. Future studies may provide even deeper insights into the role of dark matter, dark energy, and the fundamental forces shaping the universe. The Boötes void stands as a remarkable anomaly in the cosmic landscape, not only due to its sheer scale but also because of the scientific questions it raises about the large-scale structure of the universe. Spanning roughly 0.27% of the observable universe's diameter, this void defies intuitive expectations about the uniform distribution of matter. If the universe were completely homogeneous, regions as empty as the Boötes void would be highly improbable. Yet, its existence aligns with our current understanding of structure formation, demonstrating how gravity amplifies tiny density fluctuations over cosmic time. The formation of the Boötes void is tied to the broader mechanisms of cosmic evolution. In the early universe, small quantum fluctuations in the density of matter led to the formation of the cosmic web, a network of filaments and nodes connected by gravity. Regions with slightly higher densities attracted more matter, growing into galaxies and clusters, while less dense regions expanded into voids due to the gravitational pull of surrounding structures. Over billions of years, these underdense areas have become even emptier as matter continues to migrate toward the denser filaments. Cosmological simulations suggest that voids like the Boötes void emerge naturally from the lambda-CDM model of the universe. The void likely formed as smaller voids merged, reinforcing its extreme emptiness. This hierarchical merging process is analogous to how galaxy clusters grow over time. Interestingly, voids expand at a slightly faster rate than their surrounding regions because they contain less matter and experience weaker gravitational pull. This accelerated expansion makes voids unique laboratories for testing dark energy, the mysterious force driving the universe's expansion. Despite its name, the Boötes void is not completely devoid of galaxies. A sparse population of approximately 60 galaxies has been identified within its vast expanse, a remarkably low number compared to the expected density of several thousand galaxies for a region of this size. These galaxies are not randomly distributed, they appear to form small chains or filaments, suggesting that residual structure remains within the void. Some astrophysicists propose that these galaxies are survivors of an earlier cosmic epoch, having formed in regions where the density was just high enough to sustain gravitational collapse. One of the most studied galaxies in the Boötes void is MCG plus 0102-015, a relatively isolated system located near the void center. The properties of such galaxies make them interesting targets for studying star formation under conditions of extreme isolation. Unlike galaxies in denser regions, which experience frequent mergers and interactions, void galaxies evolve with minimal external influence, providing a cleaner environment to study the natural progression of stellar and galactic evolution. The Boötes void and other large cosmic voids serve as crucial testbeds for studying dark matter and dark energy. Since voids are regions where the effects of ordinary matter are minimal, they allow astrophysicists to probe the subtle gravitational influences of dark matter. Some theories suggest that voids could enhance our understanding of modified gravity models, which propose alternatives to dark matter by tweaking the laws of gravity on large scales. Additionally, voids provide insights into the nature of dark energy. The accelerated expansion of voids is consistent with the standard lambda-CDM model, but alternative explanations, such as scalar field theories or modifications to general relativity, could manifest in void dynamics. By studying how galaxies within voids move relative to their surroundings, scientists can constrain competing theories about cosmic expansion. When the Boötes void was first discovered, it seemed to challenge the standard model of cosmology, raising questions about whether such an extreme void could arise naturally. However, subsequent studies have identified numerous other large voids, including the Uranus supervoid and the northern local supervoid. Some of these voids are comparable in scale, suggesting that the Boötes void, while extraordinary, is not entirely unique. The discovery of these additional voids has strengthened the statistical case for their existence. According to simulations, cosmic voids should make up a significant fraction of the universe's volume, even though they contain relatively little mass. In fact, Voids may occupy as much as 80% of the universe's volume, with matter concentrated in the filaments and clusters that form the cosmic web. This perspective fundamentally changes how we view the universe, not as a homogeneously distributed sea of galaxies, but as a vast network dominated by emptiness. Another intriguing aspect of cosmic voids is their potential role in neutrino physics. Neutrinos, the elusive subatomic particles that barely interact with matter, are thought to play a role in shaping large-scale structures. Since voids are extremely low-density environments, they provide an ideal setting to test how neutrinos contribute to cosmic expansion and structure formation. Some speculative theories even propose that voids like the Boötes void could be associated with more exotic physics. For example, certain alternative cosmologies suggest that voids may be remnants of primordial quantum fluctuations or even regions where different physical laws apply. While mainstream cosmology explains voids through gravitational evolution, the sheer size of the Boötes void has led some to wonder whether it could hint at undiscovered cosmic phenomena. The Boötes void has also captured the imagination of the public and inspired various speculative ideas. Some have likened its vast emptiness to the hypothetical concept of a Kardashev Type 3 civilization, a civilization advanced enough to manipulate entire galaxies. While no evidence supports the idea that the void was artificially created, its extreme nature has fueled sci-fi discussions about cosmic megastructures, intergalactic engineering, and the possibility of dead zones in the universe. Philosophically, the Boötes void serves as a reminder of the vastness and complexity of the cosmos. The existence of such immense empty regions challenges our understanding of cosmic structure, compelling us to refine our models of galaxy formation and evolution. It also highlights the contrast between dense galaxy clusters teeming with activity and isolated voids where galaxies are scarce and interactions are minimal. With advancements in observational astronomy, the study of voids like the Boötes void is entering a new era. Upcoming surveys, such as those conducted by the Vera C. Rubin Observatory and the Euclid Space Telescope, will provide unprecedented insights into the large-scale distribution of voids and their role in cosmic evolution. High-resolution maps of the cosmic web will allow scientists to study the detailed structure of voids, including how their boundaries interact with surrounding filaments. Future research will also explore how voids influence cosmic microwave background (CMB) radiation. Some studies suggest that voids create subtle temperature fluctuations in the CMB due to the integrated Sachs-Wolf effect, which arises from the gravitational interaction of photons with evolving cosmic structures. By analyzing these effects, scientists may gain further insights into the nature of dark energy and the evolution of the universe. Additionally, upcoming gravitational wave observatories may provide indirect insights into the nature of voids. Since voids are low-density environments with minimal astrophysical noise, they could serve as ideal locations for detecting exotic phenomena, such as potential signatures of cosmic strings or primordial black holes. The Boötes void remains one of the most fascinating and enigmatic structures in the cosmos. Its immense scale, sparse galaxy population, and implications for cosmology make it a crucial subject of study. Whether viewed as a natural outcome of structure formation, a probe for dark energy in dark matter, or a philosophical reminder of cosmic emptiness, the Boötes void continues to inspire curiosity in scientific investigation. As observational techniques improve, our understanding of voids will deepen, shedding new light on the fundamental forces shaping the universe. The Boötes void's role in the larger cosmic landscape extends beyond its immediate structure, influencing the gravitational environment of the surrounding universe. Its vast underdensity creates a unique dynamical effect, subtly altering the movement of nearby galaxies and filaments. Because voids have less mass than their surroundings, they exert weaker gravitational attraction, allowing the structures on their periphery to expand outward at a faster rate. This phenomenon is sometimes referred to as void expansion and plays a critical role in shaping the cosmic web over billions of years. The gravitational influence of large voids like the Boötes void has been observed through peculiar velocity studies, which measure the deviations of galaxy motions from the expected Hubble flow. Galaxies on the outskirts of voids tend to experience an outward acceleration as they move away from the underdense region toward denser filaments and clusters. This motion can be detected through redshift surveys, providing an independent method for studying the large-scale distribution of matter. The study of void dynamics offers an indirect way to probe dark matter, as the rate of void expansion depends on the underlying mass distribution, including both visible and invisible components. The interaction between voids and their surroundings also affects the properties of galaxies that reside within or near them. Galaxies within voids tend to have lower star formation rates compared to those in denser environments, primarily due to the limited availability of intergalactic gas. In contrast, galaxies on the edges of voids often show signs of enhanced star formation, likely triggered by interactions as they move toward denser filaments. This suggests that void boundaries act as transition zones where galaxies undergo significant evolutionary changes, making them valuable targets for studying environmental effects on galactic development. The study of voids also intersects with research on the cosmic microwave background, CMB, the faint relic radiation from the Big Bang. Large underdense regions like the Boötes void can imprint subtle temperature fluctuations on the CMB through the integrated Sachs-Wolf (ISW) effect. As CMB photons pass through a void, they experience a slight energy shift due to the evolving gravitational potential of the underdense region. This effect provides another way to test theories of dark energy, as different models predict varying strengths of the ISW signal. Recent studies have explored whether the Boötes void contributes to the anomalous CMB cold spot, an unusually large and cold region in the cosmic microwave background, though the connection remains uncertain. In addition to their role in observational cosmology, voids have become a crucial aspect of numerical simulations aimed at understanding the formation and evolution of large-scale structures. Cosmologists use high-resolution simulations to recreate voids in virtual universes, adjusting parameters such as dark energy density, dark matter interactions, and initial cosmic fluctuations. These simulations confirm that voids naturally arise as a consequence of structure formation and that their properties can serve as a diagnostic tool for testing alternative cosmological models. Some speculative theories even suggest that voids could be linked to modifications of gravity at cosmic scales, potentially offering an alternative explanation to the lambda-CDM model. Another intriguing aspect of void studies is their potential impact on the search for exotic astrophysical objects. Because voids are largely free from strong gravitational interactions, they provide an ideal environment for detecting faint astrophysical signals that might otherwise be obscured in denser regions. Some researchers have proposed that voids could harbor primordial black holes, hypothetical remnants from the early universe that might contribute to dark matter. The lack of competing astrophysical noise in voids also makes them an interesting region for searching for hypothetical signatures of axions, weakly interacting particles that could solve outstanding problems in particle physics and cosmology. Beyond astrophysics, the Boötes void serves as a profound reminder of the universe's extreme contrasts, highlighting the balance between structure and emptiness on cosmic scales. While dense galaxy clusters form the bustling hubs of cosmic activity, voids represent the silent, vast regions where the gravitational influences are minimized, allowing a clearer view into the fundamental workings of cosmic expansion. The existence of such massive voids challenges our perception of the universe, illustrating how even emptiness plays an essential role in shaping its overall structure. Observations of the Boötes void continue to improve with advances in telescope technology. Upcoming instruments, such as the Square Kilometre Array, SKA, will provide higher resolution maps of large-scale structure, offering deeper insights into the distribution and properties of voids. Meanwhile, future space missions dedicated to studying dark energy, such as NASA's Nancy Grace Roman Space Telescope, will help refine our understanding of void expansion and its connection to the accelerated growth of the universe. The combination of observational surveys and theoretical models will ensure that voids remain at the forefront of cosmological research, pushing the boundaries of our knowledge about the fundamental nature of space and time. The possibility that voids could serve as natural laboratories for testing unconventional physics remains an open question. Some speculative ideas suggest that voids might be regions where deviations from standard physics become more pronounced. For example, certain quantum gravity theories predict that spacetime may behave differently in extremely low-density environments, potentially offering clues about the unification of gravity in quantum mechanics. While these ideas remain highly theoretical, they underscore the importance of studying extreme cosmic environments, where fundamental physics may reveal unexpected properties. In the broader context of cosmic evolution, voids like the Boötes void remind us that the universe is not a uniform sea of galaxies but a dynamic interplay between matter-rich regions and vast cosmic deserts. These immense voids, often overlooked in favor of more visually striking galaxy clusters, hold some of the most profound secrets about the forces shaping the cosmos. Their study not only enhances our understanding of cosmic structure formation but also opens new pathways for exploring the deepest questions in physics, from the nature of dark energy to the possible existence of hidden dimensions beyond our current perception. As observational capabilities continue to advance, the Boötes void and similar cosmic structures will provide an ever-expanding source of information about the past, present, and future of the universe. With each new discovery, the boundaries of our understanding shift, revealing that even in the vast emptiness of space, there are stories yet to be told. The vast emptiness of the Boötes void not only challenges our understanding of large-scale cosmic structure but also raises deeper questions about the fundamental nature of the universe. The presence of such an enormous underdense region suggests that voids may play a more active role in cosmic evolution than previously thought. While they are often seen as mere byproducts of structure formation, their unique properties, such as their accelerated expansion, weak gravitational fields, and influence on cosmic flows, may offer new insights into both standard and exotic physics. One of the most intriguing consequences of cosmic voids is their potential impact on time dilation effects in general relativity. Some theoretical studies suggest that the expansion of voids could lead to subtle relativistic effects, affecting the passage of time differently compared to denser regions of space. While these effects would be minuscule compared to those caused by strong gravitational fields, they could contribute to our broader understanding of how spacetime behaves under varying density conditions. If voids exhibit even slight deviations from the expected expansion rates, this could hint at new physics beyond the current lambda-CDM framework. Additionally, voids may act as natural magnifying lenses for rare cosmological phenomena. Since voids contain fewer foreground objects and less gravitational lensing compared to dense galaxy clusters, they offer a relatively clean view of distant quasars, cosmic explosions, and even potential transient events such as fast radio bursts, FRBs. The lack of competing gravitational distortions in void regions makes them ideal locations for detecting faint signals from the early universe, possibly revealing information about primordial black holes, ancient quasars, or even unexplored aspects of cosmic evolution. The Boötes void's extreme scale also raises questions about whether it could be linked to primordial fluctuations from the early universe. Cosmic inflation, the rapid expansion that occurred just after the Big Bang, is thought to have left behind small density variations that later evolved into the large-scale structures we see today. However, the size of the Boötes void suggests that some regions of the universe may have experienced much larger fluctuations than previously modeled. If the void originated from an unusually low-density fluctuation in the early universe, it could offer clues about inflationary physics and the conditions that governed the very first moments of cosmic history. Beyond observational cosmology, voids also provide a unique testing ground for dark matter interactions. While most dark matter research focuses on dense galaxy clusters where its gravitational effects are strongest, voids present the opposite scenario, a region where dark matter is expected to be present but in significantly lower densities. If dark matter interacts with itself or with ordinary matter in ways beyond standard gravitational attraction, voids may be the best places to observe such subtle effects. Some speculative models suggest that dark matter could have different properties in low-density environments, possibly even decaying or transitioning into exotic particles over vast timescales. The study of void galaxies, which evolve in near isolation, could help refine these theories by providing clues about how dark matter behaves in regions with minimal external gravitational influences. Another important area of research involves the potential relationship between cosmic voids and the missing baryon problem, the unresolved question of why a significant fraction of the universe's normal, baryonic, matter remains undetected. While much of this missing matter is believed to exist in the warm-hot intergalactic medium, WIM, a diffuse, ionized gas that permeates the cosmic web, voids may hold crucial evidence of its distribution. Because voids contain fewer galaxies and less luminous matter, they provide an ideal environment for detecting WIM filaments, which are otherwise difficult to observe due to their faint nature. High-resolution X-ray observations could help trace these elusive filaments, shedding light on the overall matter budget of the universe. The Boötes void also serves as a natural laboratory for studying alternative gravity models. Some modified gravity theories predict that cosmic voids should expand at rates slightly different from those expected under general relativity. Precise measurements of void expansion using large-scale surveys like the Dark Energy Spectroscopic Instrument, DESI, could help test these predictions and potentially reveal deviations from Einsteinian gravity. If such deviations were detected, they could hint at new physics governing the fundamental nature of spacetime, possibly pointing toward the existence of additional forces or extra dimensions. The study of voids is entering a new era with increasingly advanced observational techniques. The upcoming Vera C. Rubin Observatory, set to conduct the Legacy Survey of Space and Time, LSST, will provide unprecedented maps of large-scale structures, allowing for detailed investigations of void distributions and their impact on cosmic flows. Meanwhile, the European Space Agency's Euclid mission will offer high-precision measurements of cosmic expansion, helping to refine our understanding of void dynamics and their role in the evolution of dark energy. As more voids are mapped in detail, astronomers are beginning to classify them based on their unique properties. Some voids appear nearly spherical, while others have highly irregular shapes, suggesting that different formation mechanisms may be at play. There is also growing evidence that some voids may be nested within larger voids, creating a complex hierarchy of underdense regions. Understanding this hierarchy could provide further insights into how matter is distributed on the largest scales and how different cosmic environments shape the formation of galaxies and other structures. The philosophical implications of cosmic voids are equally profound. They challenge the human perception of space as something inherently full, demonstrating that the universe is dominated not by galaxies but by vast stretches of near-nothingness. This realization shifts the focus from studying what is present to understanding what is absent, making voids just as critical to cosmology as the galaxies and clusters that define the cosmic web. The study of emptiness, rather than mere absence, becomes a central theme in the exploration of the cosmos, revealing that voids are not simply empty spaces but active participants in the grand cosmic evolution. As technology improves and our observational reach extends deeper into the universe, the Boötes void will remain one of the most intriguing and enigmatic regions in the cosmos. Whether through its potential role in testing new physics, its impact on cosmic structure formation, or its ability to serve as a natural observatory for the deepest mysteries of space, the study of voids will continue to expand our knowledge of the universe's origins, composition, and ultimate fate. The Boötes void, like other cosmic voids, is not merely an empty region but an evolving structure with complex interactions at its boundaries. The outskirts of the void, where its vast emptiness meets the denser filaments of the cosmic web, serve as transition zones where galaxies experience environmental shifts. These boundary regions, sometimes referred to as void walls, are where gravitational influences from surrounding structures exert pressure on the expanding void. This dynamic interaction results in what is known as void evacuation, a process where matter is gradually pulled toward denser regions, leaving behind an ever-growing empty space. The continued expansion of voids is one of the mechanisms that contribute to the large-scale movement of galaxies, shaping the overall distribution of matter in the universe. Interestingly, void walls may also act as cosmic reservoirs for intergalactic gas. While the interior of voids is largely devoid of star-forming material, their boundaries contain diffuse filaments of hydrogen and other elements, remnants of the primordial gas that formed the first galaxies. These filaments can serve as fuel for star formation in void galaxies, albeit at a much slower rate than in denser environments. Some of the few galaxies found inside voids appear to be slowly accreting gas from these filaments, suggesting that, despite their isolation, void galaxies continue to evolve, albeit on longer timescales. One of the most intriguing questions surrounding cosmic voids is whether they could harbor exotic forms of matter or energy not yet detected in standard cosmology. Some theoretical models propose that voids might be ideal locations for studying quintessence, a dynamic form of dark energy that could vary in intensity across different regions of space. Unlike the cosmological constant model of dark energy, which assumes a uniform energy density throughout the universe, quintessence theories suggest that dark energy may have a more complex behavior, with possible variations in void environments. If voids exhibit expansion rates inconsistent with standard predictions, this could be an indirect sign of new physics governing the nature of dark energy. Another speculative idea is that voids could serve as cosmic laboratories for testing alternative interpretations of gravity. Some modified gravity theories predict that voids should expand at different rates compared to what is expected under general relativity. These effects are difficult to detect in denser regions due to the complex interplay of gravitational forces, but voids, being relatively free of such complications, provide a clearer setting to test such hypotheses. If deviations from expected void expansion rates were observed, they could hint at a deeper understanding of gravity at cosmic scales. Recent studies have also suggested that voids might be important in addressing anomalies in the cosmic microwave background, CMB. The cold spot, a large region of slightly lower temperature detected in the CMB, has been the subject of intense debate. Some researchers have proposed that a large underdense region, possibly a supervoid, could be responsible for this anomaly through the integrated Sachs-Wolf effect, in which photons passing through an evolving void experience slight shifts in energy. While the Boötes void itself is not directly linked to the cold spot, its existence supports the idea that such massive voids can influence the cosmic radiation left over from the Big Bang. Observationally, the study of voids has benefited from advancements in redshift surveys, which map the three-dimensional positions of galaxies across vast cosmic distances. Large-scale surveys such as the Sloan Digital Sky Survey, SDSS, and the upcoming Euclid mission are providing increasingly detailed maps of the cosmic web, allowing astronomers to identify and analyze void structures with unprecedented accuracy. These surveys have revealed that voids are not uniform in shape, some are nearly spherical, while others are elongated or irregular, suggesting a complex interplay of gravitational forces that shape their evolution. Void galaxies, those rare systems found in the depths of cosmic voids, continue to be a subject of interest due to their unique properties. Unlike galaxies in clusters, which experience frequent mergers and gravitational interactions, void galaxies evolve in relative isolation, making them excellent test cases for studying internal galactic processes without external interference. Some void galaxies exhibit unusually high rotational speeds, suggesting that they may contain higher proportions of dark matter compared to their counterparts in denser regions. This has led to speculation that the low-density environment of voids may influence how dark matter behaves on galactic scales. The search for faint dwarf galaxies within voids is another promising avenue of research. Dwarf galaxies are thought to be the building blocks of larger galaxies, and their distribution within voids could provide insights into early galaxy formation. Some simulations predict that voids should contain numerous faint dwarf galaxies that have failed to grow into larger systems due to the lack of external gravitational influences. Detecting these elusive galaxies requires deep imaging surveys and sensitive spectroscopic observations, which are becoming increasingly feasible with next-generation telescopes. The implications of cosmic voids extend beyond astrophysics into fundamental physics, particularly in the search for alternative explanations of cosmic acceleration. While dark energy is currently the leading explanation for the universe's accelerating expansion, some theories propose that the apparent acceleration could be an illusion caused by the large-scale distribution of voids and filaments. In these models, light traveling through underdense regions experiences different gravitational effects compared to light traveling through denser clusters, leading to observational effects that mimic cosmic acceleration. If such models were confirmed, they could reshape our understanding of the universe's expansion and the fundamental forces governing it. As the study of voids progresses, it is becoming clear that these vast cosmic regions are not mere empty spaces but dynamic components of the universe's large-scale structure. Whether through their influence on galaxy evolution, their role in testing dark energy and modified gravity, or their potential connection to fundamental physics, voids represent a frontier in cosmological research. Future observational campaigns and theoretical studies will continue to refine our understanding of voids, potentially revealing new and unexpected aspects of the universe. The Boötes void remains one of the most striking examples of these immense structures, serving as both a scientific challenge and a source of wonder. Its extreme scale, sparse galaxy population, and potential implications for cosmic evolution ensure that it will remain an important subject of study in the years to come. As our observational tools improve and our theoretical models become more sophisticated, the study of cosmic voids will undoubtedly lead to deeper insights into the nature of space, time, and the underlying fabric of the cosmos. The Boötes void and other cosmic voids not only provide a unique perspective on the large-scale distribution of matter but also raise fundamental questions about the initial conditions of the universe. One of the most intriguing ideas is whether voids could contain clues about deviations from the standard inflationary model. Cosmic inflation, the rapid expansion that occurred fractions of a second after the Big Bang, is believed to have imprinted subtle density fluctuations across the early universe. While these fluctuations led to the formation of galaxies and clusters, they also contributed to the emergence of voids. However, the Boötes void's exceptional size has led some researchers to wonder whether it could be the result of an unusually large primordial underdensity, one that deviates from standard Gaussian fluctuations predicted by inflation. If such a deviation were confirmed, it could have profound implications for our understanding of the early universe. Some alternative inflationary models predict the existence of large-scale non-Gaussian features, meaning that the density fluctuations responsible for galaxy formation may not have been purely random but instead influenced by unknown physics during the earliest moments of cosmic history. Detecting such anomalies within void structures could provide insights into the conditions that existed before the universe became transparent to radiation, offering a glimpse into physics beyond the observable horizon. In addition to their potential connection to early universe physics, voids may also serve as windows into the nature of the cosmic neutrino background. Neutrinos, nearly massless particles that rarely interact with matter, were once thought to have little impact on cosmic structure formation. However, their tiny but non-zero mass means that they move at relativistic speed in the universe, suppressing the formation of small-scale structures, while allowing larger structures like voids to expand more freely. By studying the properties of voids, cosmologists can place tighter constraints on the total neutrino mass and determine whether exotic neutrino propagates sterile neutrinos or interactions beyond the in shaping the cosmos. The influence of voids extends even further into matter, particularly its distribution under extreme conditions. Observational efforts to study dark matter focus on galaxy clusters, where gravitation provides direct evidence of unseen mass. Voids offer an entirely different approach, regarding how dark matter. Researchers can examine how it behaves in regions of near emptiness. If dark matter has non-gravitational interactions or exhibits properties such as self-interaction or decay over cosmic time, voids may be one of the best places to detect such effects. Any anomalous gravitational behavior within voids compared to denser regions could hint at deviations from the conventional cold-dark matter paradigm. Another speculative but intriguing possibility is that voids might act as conduits for detecting hypothetical cosmic structures, such as domain walls or cosmic strings. These relics from the early universe, if they exist, could manifest as large-scale gravitational anomalies influencing the motion of galaxies near void boundaries. While no direct evidence for such structures has been found, voids provide a natural testing ground for these ideas, as they are relatively undisturbed environments where even subtle gravitational effects could be more easily detected. On an observational level, upcoming missions such as the Vera C. Rubin Observatory and the Euclid satellite will provide increasingly detailed maps of the cosmic web, allowing researchers to refine void catalogs and study their properties with unprecedented precision. These surveys will help determine whether void expansion rates match theoretical predictions or if there are unexpected variations that could hint at new physics. High-resolution WIS, which measure tiny distortions in background light due to intervening mass distributions, will also allow for modeling of void potentially revealing substructures that were previously. The potential for voids to reveal new aspects of physics is not limited to fundamental cosmology. There are also implications for astrophysical processes occurring within them. While void galaxies are rare, those that do exist offer to study star formation in minimal external influences. Some void galaxies exhibit unusually high rates of star formation compared to leading to speculation that their isolation may result in a prolonged retention of gas, allowing them to sustain over longer time. Studying these galaxies could provide insights into the role of environmental factors in galactic evolution and whether void galaxies represent an earlier stage in the formation of larger systems. Beyond individual galaxies, the intergalactic medium, IGM, within voids may also hold important clues about cosmic evolution. While the IGM in denser regions is often ionized by radiation from active galaxies and quasars, voids may contain pockets of neutral hydrogen that have remained relatively undisturbed since the cosmic dawn. Detecting such pristine gas could offer a unique opportunity to study the conditions of the early universe, potentially revealing information about the reionization epoch, the period when the first galaxies and quasars ionized the surrounding hydrogen, transforming the universe into its present state. The Boötes void, despite its remoteness and emptiness, serves as a reminder that the universe is shaped not only by what is present, but also by what is absent. Voids represent the silent, expanding structures that influence the motion of galaxies, the behavior of dark matter, and the properties of the cosmic expansion itself. They are not simply regions of nothingness but active participants in the evolution of the cosmos, shaping the grand narrative of structure formation in ways that are still being uncovered. As new observational techniques and theoretical models continue to refine our understanding, voids will remain at the forefront of cosmological research. Their study has the potential to unlock new perspectives on everything from the nature of dark energy to the possibility of physics beyond the standard model. The Boötes void, as one of the most extreme examples of such structures, will undoubtedly continue to inspire scientific inquiry, challenging our understanding of the universe, while revealing the hidden forces that govern its vast and mysterious expanse. The continued investigation of the Bootes void also challenges us to rethink the role of statistical outliers in cosmology. In a universe governed where density fluctuations from quantum origin caused by inflation, extreme structures like the Bootes void are not necessarily violations of the model, but rather its most striking predictions. These rare cosmic events, occurring at the far tails of probability, are testing the robustness of our cosmological framework. If structures in this void appear more frequently or exhibit properties inconsistent with simulations on lambda, it could signal new physics or a refinement of initial assumptions. There is also a growing interest in exploring the relationship between voids and cosmic topology, the study of the universe's global geometric properties. Some cosmologists have proposed that the large-scale arrangement of voids, filaments, and clusters could reflect deeper aspects of the universe's shape and connectivity, potentially even hinting at a non-trivial topology. If the universe wraps around itself in higher dimensions in some compact topology models, patterns in the distribution of voids could offer indirect evidence. Analyzing the large-scale coherence, orientation, and alignment of voids might one day help answer the profound question of whether the universe is finite or infinite in extent. Moreover, the acoustic signatures of voids, particularly their imprint on baryon acoustic oscillations, BAO, offer another tool for cosmologists. BAOs are relic patterns of sound waves that move through the early universe's plasma before recombination. These waves left a subtle but detectable imprint on the distribution of galaxies and matter. While most BAO studies focus clusters, voids also contain this signal, albeit inverted. Analyzing the BAO signal in voids provides a complementary and independent measure of the expansion history of the universe, allowing researchers to further constrain the equation of state of dark energy and test the consistency of cosmological parameters. In the computational realm, the modeling of voids has become increasingly sophisticated. Modern cosmological simulations can now resolve both the vast scales of voids and the finer details of the galaxies within them. These simulations incorporate not only gravitational dynamics, but also complex baryonic processes such as gas cooling, star formation, and feedback from supernovae and black holes. By comparing observed void properties with those from simulated universes, scientists are able to fine-tune models and rule out parameters or processes that reproduce the real universe. In this way, voids act as powerful calibration tools for refining mental models of cosmic evolution. Another dimension to void research lies in the emerging field of void lensing. Though voids are underdense, their cumulative gravitational effect can still influence the path of light traveling through or near them. This weak lensing effect is extremely subtle, far less dramatic than the strong lensing seen near massive clusters, but with detecting and analyzing void lensing helps map the distribution of mass in and around voids, offering indirect insights into the dark matter component that dominates the universe's mass budget. Combined with galaxy dynamics and redshift space distortions, void lensing adds another layer to our ability to probe gravity and structure formation. On the frontier of observational astrophysics, new techniques are being developed to probe the gas content within voids. Instruments capable of detecting faint Lyman alpha absorption features from background quasars are helping to reveal the distribution of neutral hydrogen and ionized gas in these vast regions. By mapping how this gas evolves over cosmic time, researchers can reconstruct the history of matter flow from the early universe to the present day. These observations also test predictions from hydrodynamics and provide a clearer picture of how the intergalactic medium behaves under different environmental conditions. From a philosophical and anthropic perspective, the Boötes void adds depth to the contemplation of our cosmic position. Humanity exists in a region of the universe where galaxies, stars, and heavy elements are abundant, a place where life, as we know, is necessary to arise. But most of the universe, as evidenced by regions like the Boötes void, is vastly different, quiet, cold, nearly empty, and almost entirely sterile. The existence of such immense voids underscores the rarity and fragility of the conditions that allow life to flourish. It raises existential questions about cosmic isolation and the likelihood of other intelligent civilizations emerging elsewhere, especially in such barren zones. This has even sparked speculation in the context of the Fermi paradox, the question of why, given the vastness of the universe, we have not yet observed signs of extraterrestrial intelligence. Some thinkers have wondered whether large voids could represent deserts in the galactic ecosystem, where the emergence of complex life is statistically improbable due to environmental isolation. In such a view, the Boötes void might not only be physically empty but biologically as well, a reminder that life-supporting conditions are concentrated in only select corners of the cosmic web. In the end, the Boötes void remains a canvas onto which cosmologists, astronomers, physicists, and philosophers alike project a structure born from gravitational, shaped by primordial fluctuation, expanded by the unseen force, and now studied by the scientific instrument has ever illness, and its scales speak to the immensity of the cosmos and the journey of discovery that propels our understanding of it forward. As researchers delve deeper into the Boötes void and its analogues, attention is increasingly turning to the role these immense underdense regions may play in defining the boundaries of cosmic evolution itself. Rather than being passive absences of matter, voids may act as dynamic components within the cosmic web, not only their immediate surroundings but also the statistical behavior of structure formation on the largest scales. One emerging area of research involves the concept of cosmic back reaction, the idea that local inhomogeneities, like voids and clusters, could cumulatively influence the expansion rate of the universe. While standard cosmology assumes that variations average out over large volumes, Some researchers argue that the growth of voids could observe the acceleration of cosmos. This idea remains controversial, and Boötes void offers a real-world laboratory for such effects and testing whether the standard assumptions about cosmos. Furthermore, like Boötes are essential for the whole life cycle of matter in the universe. Galaxies or near voids sites into systems. Without frequent mergers or environmental these galaxies often retain more primordial characteristics, such as simpler morphologies, extended Hi gas disks, and lower metallicities. By examining these astronomers can conditions of the early universe and trace the relatively undisturbed pathways of galaxy growth. In this sense, void galaxies may serve as time capsules, preserving evolutionary histories that are erased or overwritten in more crowded cosmic neighborhoods. The chemical composition of void galaxies also contributes to this picture. Spectroscopic studies have revealed that void galaxies tend to have fewer heavy elements, metals, than clusters and groups. Metallicity supports the idea galaxies experience gradual star formation, allowing for a more pristine environment in which the early conditions are reflected in the present. This makes them valuable targets for chemicals, helping scientists elements are produced across time and space. There is also a practical observational benefit to the study of voids. They provide clear lines of sight through the universe. In denser regions, the intergalactic medium is often crowded with gas, dust, and intervening galaxies that obscure or distort the light from distant sources. Voids, by contrast, offer relatively unobstructed pathways through space, enabling more precise observations of high redshift objects, gravitational waves, and background radiation. These low-opacity windows into the cosmos can be used to study quasars, gamma-ray bursts, and the faint glows of the early universe, free from much of the foreground interference that complicates observations elsewhere. In the context of dark energy research, voids present sensitive tools available for detecting deviations from standard cosmological behavior. Because voids are effectively pressureless environments, the way in which they expand and evolve is governed primarily by the geometry of space and the properties of dark energy. If time or behaves differently across different environments, these could dynamics. Ongoing efforts to measure shapes and rates of voids over cosmic time effects and variations in the darkness of officially applied to the classification and analysis of cosmic voids. Enormous datasets generated by current and future galaxy surveys, traditional methods of void identification are being supplemented by automated algorithms that can detect subtle void structures across vast cosmic volumes. These tools are also capable of identifying correlations between void properties and other cosmic observables, such as galaxy bias, halo occupation distribution, and redshift space distortions. By observational data with simulation, AI is opening new avenues for high cosmology. The sheer psychological impact of the Boötes void continues to echo beyond the domain of science. For many, it symbolizes the vastness and the humbling realization that most of cosmic space is perfectly empty. Philosophers and writers have drawn inspiration from the idea that even in a universe filled with light and matter, it is the dark and silent spaces that dominate. The Boötes void, stretching for hundreds of millions of light-years with only a handful of galaxies scattered, becomes a metaphor for the loneliness of existence, or, alternatively, for the elegant simplicity of nature's grand design. In science fiction and speculative thought, voids have become associated with the unknown. Some fictional works imagine them as hiding places for ancient civilizations, dimensional rifts, or relics of failed universes. While such ideas lie outside the boundaries of empirical science, they reflect a human tendency to imbue the cosmos with meaning, to see in the emptiness not just the absence of matter, but the potential for mystery or revelation. Returning to the realm of science, it's important to note that the boundaries of voids are not static. They grow and evolve over time by the flow of matter barriers and toward denser regions. This movement, called large-scale cosmic flow, is not only a key prediction of cosmological models but also a measurable phenomenon. Observing the velocities of galaxies near void edges can map the gravitational influence of voids and verify how closely these flows align with theoretical predictions. In these flow patterns could signal the unknown forces or particles, offering yet another potential window into aspects of cosmic physics. The challenge look deeper into the structure of the universe, but to refine our methods, theories, and confront our assumptions. It reminds us that what we do not see may be as important as what we do, that the gaps in the cosmic web, the dark spaces between the stars, and the vast volumes between galaxies are not empty of meaning, but filled with clues to the deepest workings of reality. The Boötes void continues to serve as a gravitational and conceptual anchor in the growing exploration of cosmic voids, illuminating the hidden architectures. While traditional efforts have focused on galaxy clusters, quasars, and other bright, energetic regions, voids offer an inverse perspective, one that foregrounds the role of absence, silence, and expansion in the formation and evolution of cosmic structures. As voids grow, they contribute to the overall anisotropy of the cosmic web. This evolving asymmetry introduces subtle, large-scale features that may influence everything from alignments to the direction of flows. Recent studies suggest that the orientations of galaxies and even the spin vectors of dark matter halos can be correlated with their position relative to nearby voids. This void-induced alignment effect hints at a deeper interconnectedness between the geometry of space and the evolution of cosmic systems. If confirmed, such findings could redefine the way cosmologists think about the environment, lending support to the idea that even in the vast empty, structural memory and directional imprinting persist. These patterns could also help to explain certain anomalies in cosmic isotropy. While the cosmological principle assumes the universe is homogeneous and isotropic, increasingly precise observations have revealed potential large-scale asymmetry and galaxy distributions. Though still under debate, these cosmic hemispheric asymmetries may be linked to the statistical presence or configuration of enormous voids and superclusters across the observable universe. The Boötes void, exceptional scale, has become a reference point in these discussions, a test case for understanding whether large-scale inhomogeneities may hint at a deeper anisotropic fabric to space-time. Another emerging frontier is the study of the intervoid regions, the connective zones between multiple voids. These tenuous corridors of extremely low-density matter are among the least understood environments in the universe. Simulations predict that these ultra-diffuse bridges may contain traces of dark matter filaments or warm-hot baryonic material too faint to detect through traditional means. By targeting regions between large voids, astronomers hope to detect the faint signatures of the missing baryons, thought to reside in these nearly invisible structures. This endeavored cosmology for the hidden cosmic inventory. The intersection of void studies with time-domain astronomy is also a promising field. Because voids are gravitationally quiet and contain few astrophysical sources, they may provide ideal backgrounds for the detection of transient phenomena. Fast radio bursts, high-energy neutrino events, or even hypothetical technosignatures, if they occur within or traverse void regions, may be more easily identifiable due to the minimal noise and interference. Monitoring these dark expanses could reveal not only new phenomena, but also clarify the nature and distribution of known transients. Meanwhile, cosmological simulations are entering a new phase of resolution and complexity, allowing for the modeling of voids not just as simple underdensities but as rich, dynamic substructure, thermal, and internal flows. The so-called void hierarchy is now being explored, the idea that voids contain smaller voids within them, nested across scales, forming a fractal-like structure in space. This multi-layered emptiness defies earlier assumptions that voids are relatively featureless. Instead, a void may have its own filaments, walls, and nodes, much more subtle scale. This hierarchy of emptiness could have implications for entropy and information distribution in the universe. Theorists have speculated, by being the endpoints of structure evolution, regions without and rarely could serve as natural voids of low and radiation over billions of years. As galaxies age, stars burn out, and black holes evaporate, more of the universe will begin to resemble the Boötes void, not just in structure, but in thermodynamic character. In this far-future scenario, voids are not the exception. As cosmic acceleration continues to separate gravitationally bound systems, isolated and galaxy groups are growing. The Boötes void, then, as a prototype for the late universe, a preview of the conditions that will dominate when star formation has ceased, matter has dispelled longing philosophical scales, the Boötes evokes reflection. It is a boundary between presence and absence, between the luminous and the hidden, between the known and the unknowable. And yet it becomes not but of processes silence and will scale. The study of voids in ways, the study of space itself, its geometry, its structure, its evolution. And it reveals, again and again, that emptiness is not the absence of structure, just Boötes void of information about the forces that sculpted the universe, about the past and future of matter and energy, and of our own understanding. As astronomers continue to map the cosmos in ever greater detail, the Boötes void will remain a profound frontier, not just in physical space, but in intellectual space as well. A frontier where darkness is not ignorant. In the end, the Boötes void is not merely a vast emptiness, it is a cosmic mirror, reflecting the universe's deepest processes and quietest truths. Its silence speaks of structure, its darkness of evolution. As one of the universe's grandest voids, it reminds in the absence of matter and meaning. The study of such clues to expand, not just of the cosmos, but of our place within it.
Is one of the most mysterious and fascinating planets in our solar system, a world that continues to puzzle scientists and inspire. It is the seventh planet from the Sun, orbiting at an average distance of about 2.87 billion kilometers, 1.78 billion miles. This icy giant stands out not only for its composition and unique features, but challenges it poses to our understanding of planetary science. Discovery 1 by William Herschel, Uranus was the first planet found with the aid of a telescope. Unlike the 5 planets visible to the naked eye, Uranus marked the expansion of our cosmic horizons. Initially thought to be a star or comet, it was later confirmed as a planet, fundamentally changing how humanity viewed. One of the most striking characteristics of Uranus is its extreme axial tilt of 98 degrees. Unlike other planets, which are upright relative to their orbits, Uranus essentially rolls along its orbit, spinning on its side. This unique orientation creates extreme seasonal variations. Each pole experiences 42 Earth years of continuous sunlight, followed by 42 years of darkness. Scientists are still trying to fully understand the origin of this tilt, with the prevailing theory suggesting a massive collision with an Earth-sized object early in. Uranus is classified as an ice giant, along with its sibling Saturn are dominated by hydrogen and helium, as a higher proportion of ices, such as ammonia and methane in its interior. This methane is also responsible for the planet's pale, as it absorbed flex blue. The planet's color is less vivid compared to Neptune, possibly due to differences in atmospheric haze. Uranus' calm appearance lies in turbulent atmosphere. The supersonic winds reaching speeds of up to 9 miles per hour, 560 miles per hour. Its temperature drops to a frigid minus 200 degrees Celsius, 171 degrees Fahrenheit, making it in the solar system. Despite its icy nature, it emits very little internal heat compared to other planets. This lack of heat flow is another mystery, as it suggests a unique thermal evolution. It also has a complex magnetic field, tilted from its rotational axis, planet's center. A relatively symmetrical magnetic field, its magnetosphere is lopsided and highly dynamic, causing its mag wander unpredictably. This field interacts with the solar wind to produce unusual auroras, which differ greatly from those observed on Earth and Jupiter. By a system of 13 faint rings and 27 known moons, all named after characters from Alexander Pope's works. The rings are composed of icy and rock, possibly remnants of a comet. Among its moons, Titania and Oberon are the largest, with intriguing surfaces and possibly activity. Exploration of Uranus has been led by of NASA's craft in 1986. During its brief encounter, 2 provided a wealth of data, revealing detailed atmosphere, rings. However, much remains unknown. Jupiter and Saturn, Uranus has not been revisited by spacecraft, leaving it as one of the least studied planets in the solar system. Future missions to Uranus are a high priority for planetary scientists. Missions could provide insights into the formation and evolution of ice giants, which are among the most common types of planets in our galaxy. Understanding Uranus could also shed light on exoplanets or characteristics. Key goals include investigational structure, atmospheric dynamics, magnetic field, surface oceans on its moons. Challenges our understanding of planetary systems. Characteristics, from its extreme tilt to its dynamic, mysterious interior, target for exploration. As technology space agencies plan new missions, the icy giant may finally reveal, enriching not only the solar system but all planets in the universe. Uranus, 7th planet from the Sun, one of the most intriguing world system. This ice giant, located approximately 2.9 kilometers, 1.78 billion miles, from the Sun, conforms with its unique features, baffling scientists and captivating centuries. Discovered in 1780, German-born British official, Uranus was the first planet aid of a telescope. Discovery was revolutionary, expanding the known bound system and marking the beginning of modern planetary astronomy. Initially thought to be a comet or star, its true nature as a planet was confirmed by observation, altering understanding of the cosmos. One of Uranus's most striking features is its tilt of approximately 98 degrees. Unlike any other planet in the solar system, Uranus spins almost on its side. Poles face the sun at different points, leading to extreme and prolonged. Each pole experiences 42 Earth years followed by 42 years of darkness, creating a climate like anything on Earth. Theorized that this tilt resulted from a colossal-sized object during the early stages of the planet's formation. Uranus is classified as an ice giant, neighbor Neptune. While Jupiter is dominantly composed of hydrogen and helium, Uranus has a higher concentration, which include water and methane. These substances extreme pressure within the planet's interior, contributing to its use. The methane in its upper atmosphere absorbs red light. Uranus, its pale blue color. However, its hue is less vibrant than possibly due to differences in atmospheric haze or chemical composition. The sphere of Uranus is a dynamic environment with winds of up to 900 km, 560 miles per hour, planetary atmosphere system, with minimum temperatures plunging 224 degrees Celsius, minus 371 degrees. This frigid environment questions about the planet's thermal history, as Uranus emits surprising heat compared to other giants. Another fascinating aspect is its complex and asymmetric magnetic. Unlike Earth, where the magnetic field is relatively aligned with the axis, Uranus' field is tilted by about 59 degrees from its center. An irregular field auroras and interacts with the solar remain poorly understood. The only space revealed this peculiar magnetic during its 1980s, leaving scientists detailed exploration. Surrounded by a faint ring consisting of rings primarily composed of dark particles. Rings are far less prominent than Saturn's, fascinating and possibly formed from shattered moons or remnants of. Beyond it, Uranus has 27 known moons, all named from Shakespearean Pope's works. The largest moons, Titan, Ariel, and Miranda, worlds within creatures, includes impact and possibly even subsurface oceans. The moons of Uranus hold particular interest to biologists. Some, and Titania, may host oceans beneath their icy crusts. These oceans could contain the necessary conditions for such as liquid water and organic molecules. Understanding is a key goal for future exploration, as they could shed light on the potential for habitability elsewhere. System. This significance means one of the leads in the solar system. Jupiter's breeded valuable data, reached the surface of understanding world. Scientists advocate for a dedicated mission to Uranus, which are an atmospheric probe's composition, weather patterns, and moons. Such a mission would also enhance our understanding of ice giants, which are among of planets discovered in other star systems. The study of Uranus is not just about understanding one planet. It is about gaining broader processes that govern planetary formation and evolution. Giants like Uranus challenge our models of planetary interiors, atmospheres, and magnetic fields. Moreover, study could provide context for interpreting observations of similar characteristics. Mission could revolutionize our outer solar system. With advanced instruments could map, analyze its atmosphere, and study its moon. Unprecedented. Such a mission requires innovative technologies, including nuclear-powered systems to sustain operations in the dim sun. Uranus is of the outer solar system, challenging beyond conventional models and explore the unknown. Extreme tilt, frigid complex magnetic field, and potential subsurface oceans make it for future. By unlocking the secrets of Uranus, humanity may uncover fundamental the formation and evolution of planetary systems, solar system and beyond. Of Uranus, its potential planetary systems beyond our own. Thousands of exoplanets have been discovered, stars, and a significant giant analog planets similar in size and mass to Uranus and Neptune. Studying Uranus in detail, reference point for interpreting data results, determine their atmospheric composition, internal structures for hosting life. One of the most aspects of Uranus of mission. Unlike Jupiter, Saturn, which radiate more heat than the Sun, Uranus emits almost no detectable internal heat. This is about the planet's formation and thermal evolution. Theories suggest that Uranus experienced a cataclysm during its early history, not only caused its extreme but also disrupted its infusion, effectively locking in its cold state. anomaly could reveal new thermal dynamics of ice giants in the protoplanetary disk. The planet's atmosphere is another scientific curiosity. Beneath its calm blue complex and chemical reactions, observations from Earth-based telescopes and the Hubble Space Telescope, bright spots and cloud systems that indicate dynamic weather patterns, suggest that external heat has an active seasonal changes and possibly unknown process within the planet. Future mission high-resolution imaging and spectroscopy more detailed picture of these atmospheric phenomena. The rings and moons of Uranus are targets for unlike Saturn. Uranus's rings are dark and sparse, of organic-rich materials, and remains a mystery formed from ancient, or are they remnants of the planet process? Answering these questions could illuminate the shaped the outer. Uranus's moons, Haumea and Oberon, are prime candidates for. These moons are larger dwarf planets if independently. Their surfaces, craters, rifts, and other features hint at a complex history of tectonic cryovolcanic activity. Conditions may exist on some of these moons, mutual heat, and the presence of antifreeze compounds. Exploring these moons, valuable clues acquire the potential for habitable environments on icy worlds. Moreover, Uranus's magnetic field adds another layer of complexity to its study. The tilted, offset nature of the field suggests that the planet's dynamo, a mechanism in its interior that generates the magnetic field, is fundamentally different from that of Earth or the gas giants. Understanding how this dynamo operates under the extreme pressures and compositions of Uranus's interior could expand our knowledge of planetary magnetism across a wide range of celestial bodies. The technology needed to explore Uranus poses its own set of challenges. Given its vast distance from the Sun, any spacecraft sent to Uranus must rely on nuclear-powered systems, such as radioisotope thermoelectric generators, RTGs, to function effectively in the dim light and frigid temperatures of the outer solar system. Communications delays of about 2.7 hours each way will also require advanced autonomous systems capable of conducting scientific operations without constant input from Earth. NASA and other space agencies are actively considering missions to Uranus, recognizing its scientific importance. A dedicated orbiter and atmospheric probe could revolutionize our understanding of ice giants, building on the limited but tantalizing data provided by Voyager 2. By diving into Uranus's atmosphere, the probe could directly measure its composition, temperature, and pressure, providing data that is impossible to obtain from Earth. Meanwhile, an orbiter could map the planet's magnetic field, study its rings and moons, and monitor its atmospheric activity over time. Exploring Uranus is about more than just unraveling the mysteries of a single planet. It is a journey to understand the processes that shape the diversity of planetary systems across the galaxy. Ice giants like Uranus are thought to form in specific regions of protoplanetary disks, migrating over time to their current positions. By studying Uranus, we can refine our models of how planets form, migrate, and interact within their systems. In the coming decades, as humanity ventures further into the cosmos, Uranus will likely play a central role in expanding our knowledge of planetary science. Its unique characteristics, extreme axial tilt, icy composition, unusual magnetic field, and dynamic moons, make it a natural laboratory for uncovering new phenomena. By exploring this distant world, we not only deepen our understanding of our own solar system, but also gain a glimpse into the nature of countless other planetary systems that populate the universe. Uranus reminds us that even in our own cosmic backyard, there is so much left to discover. Each step toward its exploration brings us closer to answering fundamental questions about the origins and workings of planets, the potential for life beyond Earth, and the intricate dynamics of the cosmos itself. This icy giant, silent and distant, holds the keys to unlocking some of the most profound mysteries of existence. The potential for Uranus to unlock profound cosmic mysteries cannot be overstated. Despite its silent and distant presence, it holds answers to questions that extend far beyond our solar system. To truly grasp the significance of Uranus, we must delve deeper into what its exploration could reveal, not only about itself but about the nature of planetary systems and the broader universe. One of the most exciting prospects in studying Uranus lies in its connection to the field of comparative planetology. Ice giants like Uranus and Neptune occupy a middle ground between terrestrial planets, such as Earth and Mars, and the gas giants Jupiter and Saturn. This intermediate category bridges the gap in our understanding of planetary formation and evolution. By comparing Uranus with other planets, scientists can refine their theories about how planets develop over time, why their compositions vary, and how they interact with their environments. For instance, the atmospheric dynamics of Uranus are a puzzle waiting to be solved. Unlike Jupiter and Saturn, whose atmospheres are dominated by powerful storms and heat-driven convection, Uranus appears deceptively calm on the surface. However, its atmosphere is far from static. Infrared observations reveal complex cloud structures, likely composed of methane, ammonia, and water ice. These clouds, combined with supersonic winds and temperature inversions, hint at hidden processes driving atmospheric circulation. Understanding these dynamics could help scientists model atmospheres on distant exoplanets with similar compositions. Speaking of exoplanets, Uranus is an invaluable analog for studying planets beyond our solar system. Many of the exoplanets discovered to date fall into a category known as mini-Neptunes or sub-Neptunes, which are similar in size and composition to Uranus and Neptune. These planets are among the most common types in our galaxy, yet they remain poorly understood because we lack detailed observations of similar planets in our own system. By studying Uranus, we gain a Rosetta Stone for interpreting data on these distant worlds, helping us unlock their atmospheric compositions, internal structures, and potential for habitability. Another fascinating aspect of Uranus is its potential to host unique chemistry within its interior. The extreme pressures and temperatures inside Uranus may create exotic states of matter, such as superionic water, where hydrogen ions move freely within a lattice of oxygen atoms. This phase of water, which behaves like a conductor, could play a crucial role in generating Uranus's unusual magnetic field. Additionally, carbon within Uranus's interior might form diamonds, which could sink to the core in a diamond rain phenomenon. These processes are not only captivating in their own right, but also provide critical insights into how materials behave under extreme conditions. Uranus's moons add yet another layer of intrigue to its study. Each of its major moons, Titania, Oberon, Ariel, Umbriel, and Miranda, offers a unique geological story. Miranda, for instance, has one of the most unusual and varied surfaces in the solar system, featuring ridges and possibly evidence of cryovolcanism. Titania and Oberon, the largest moons, may harbor subsurface oceans, raising the possibility of environments capable of supporting microbial life. If confirmed, these moons could join the ranks of other ocean worlds in the solar system, such as Europa and Enceladus, as prime targets in the search for life. To explore Uranus effectively, future missions will need to leverage the latest advancements in technology and engineering. An orbiter equipped with instruments such as spectrometers, magnetometers, and imaging systems could conduct detailed surveys of the planet and its moons. A descent probe could directly sample the planet's atmosphere, providing data on its composition, temperature, and pressure gradients. Such a mission would represent a monumental leap in our understanding, comparable to the groundbreaking studies of Jupiter by the Juno spacecraft or Saturn by the Cassini-Huygens mission. The logistical challenges of reaching Uranus are significant but not insurmountable. Its vast distance from the Sun means that spacecraft must be equipped with power sources like radioisotope thermoelectric generators, RTGs, which can operate in low-light conditions. The journey itself, lasting 10 to 15 years depending on the launch window and trajectory, requires precise planning and execution. However, the scientific payoff would be immense, offering decades of data to analyze and interpret. Looking ahead, Uranus could also become a stepping stone for future exploration of the outer solar system. A mission to Uranus would serve as a testbed for technologies and techniques needed to explore even more distant worlds, such as Neptune and its largest moon, Triton. It could also pave the way for interstellar exploration by demonstrating our ability to operate spacecraft effectively at extreme distances from the Sun. Ultimately, Uranus reminds us of the boundless potential for discovery that lies within our own cosmic neighborhood. Every detail we uncover about this enigmatic planet, its atmosphere, interior, magnetic field, rings, and moons, adds another piece to the puzzle of how planets form, evolve, and interact. In studying Uranus, we not only deepen our understanding of the solar system, but also take steps toward answering some of the most profound questions about the universe. How common are planets like Earth? Could life exist elsewhere? What forces shape the cosmos we inhabit? The exploration of Uranus is not just an academic pursuit. It is a testament to humanity's unyielding curiosity and drive to explore the unknown. As we continue to push the boundaries of knowledge, Uranus stands as a beacon of possibility, inviting us to uncover its secrets and, in doing so, illuminate the mysteries of the universe. The journey to Uranus is not just a scientific endeavor, but also a philosophical one. It represents our quest to understand our place in the cosmos and our connection to the processes that have shaped the solar system. Uranus, with its peculiarities and mysteries, offers a unique lens through which we can view the broader dynamics of planetary systems. One of the most profound questions that Uranus could help answer concerns the formation of ice giants. While the gas giants Jupiter and Saturn formed closer to the Sun and accumulated massive hydrogen and helium atmospheres, ice giants like Uranus and Neptune likely formed farther out, where water, ammonia, and methane could condense into solid ice. These volatile-rich planets might have formed their cores first, later capturing a thinner atmosphere of hydrogen and helium. But why did Uranus and Neptune stop growing, while Jupiter and Saturn continued to accumulate gas? And how did their migration to their current positions influence the development of the entire solar system? By studying Uranus's internal structure, scientists hope to uncover clues about this process. Current models suggest that the planet's interior is composed of a rocky core, surrounded by a thick layer of water, ammonia, and methane ices, and enveloped by a relatively thin hydrogen-helium atmosphere. However, there are significant uncertainties. For example, Uranus's lack of internal heat emission raises questions about its energy balance. Did an ancient collision disrupt its interior and scatter its heat outward, leaving it colder than expected? Understanding Uranus's thermal history is essential for piecing together the puzzle of its formation. Uranus's moons, too, hold keys to the planet's past. These natural satellites are not just passive companions. They interact dynamically with Uranus and its ring system. Tidal forces between the planet and its moons may heat their interiors, potentially sustaining subsurface oceans. Ariel, with its bright surface and apparent lack of craters, suggests recent geological activity, while Titania's large canyons hint at tectonic forces that reshaped its surface. Miranda, the smallest of the major moons, features enormous cliff faces and terrain so varied that it looks as though the moon was torn apart and reassembled. Each moon has a story to tell about the processes that shaped Uranus and its surroundings. The magnetic field of Uranus is another enigma. Unlike the relatively aligned magnetic fields of Earth and Jupiter, Uranus's field is tilted and off-center. This irregularity suggests that the dynamo generating the magnetic field is located in a shallow region of the planet's interior, possibly in its icy mantle. Such a configuration challenges traditional models of planetary magnetism and raises broader questions about how magnetic fields are generated in planets of different compositions and sizes. The potential for life on Uranus or its moons is an intriguing prospect, albeit a challenging one to evaluate. While the planet's extreme cold and lack of a solid surface make it inhospitable for life as we know it, its moons may tell a different story. Subsurface oceans, if present, could provide environments where life might exist. These oceans would be shielded from the harsh radiation of space and could contain the chemical ingredients necessary for life, driven by hydrothermal activity or tidal heating. Uranus also provides a unique opportunity to study planetary rings. Unlike Saturn's bright and expansive rings, the rings of Uranus are narrow, dark, and composed of material that absorbs more light than it reflects. Their origin is uncertain. Did they form from the debris of shattered moons, or are they remnants from the planet's formation? The ring's composition and dynamics could reveal new information about the evolution of the Uranian system and the forces that shape ring systems throughout the solar system. As space agencies plan future missions, Uranus emerges as a priority destination. NASA, for instance, has identified Uranus as a high-priority target for exploration in its decadal survey. A mission to Uranus could include an orbiter to study the planet, its rings and moons in detail, as well as an atmospheric probe to dive into its clouds and measure their composition and structure directly. This mission would not only answer questions about Uranus itself, but also pave the way for exploring other ice giants like Neptune, broadening our understanding of this class of planets. In the context of exoplanet research, Uranus serves as a critical benchmark. Many of the planets discovered around other stars fall into size categories similar to Uranus and Neptune, yet these mini-Neptunes remain poorly understood. By studying Uranus in detail, we gain insights that can be applied to these distant worlds. For example, understanding the atmospheric processes of Uranus could help interpret the spectra of exoplanets, revealing their atmospheric compositions and potential climates. Uranus also represents a step toward answering one of humanity's oldest questions. Are we alone in the universe? While the icy moons of Uranus are less well-studied than Europa or Enceladus, they could harbor conditions favorable to life. The discovery of even microbial life beneath the icy crust of a Uranian moon would have profound implications for our understanding of biology and its prevalence in the cosmos. In the grander scheme, Uranus is a reminder of how much there is left to explore. It challenges us to think beyond our familiar world, to push the boundaries of science and engineering, and to embrace the unknown. The mysteries of Uranus are not just puzzles to be solved. They are invitations to expand our horizons, to see the universe in new ways, and to deepen our appreciation for the complexity and beauty of the cosmos. As humanity looks toward the stars, Uranus stands as a gateway to the next great era of exploration. Its secrets, waiting to be uncovered, promise to enrich our understanding of the solar system and inspire generations to come. From its tilted axis to its icy moons and beyond, Uranus is a world that reminds us that the universe is full of wonders, just waiting for us to discover them. The exploration of Uranus is a story that stretches from our earliest understanding of the cosmos to the cutting-edge science of today, with the promise of even greater revelations in the future. To fully appreciate Uranus, we must consider not only what we know, but also the vast realms of the unknown it represents. Realms that invite curiosity, innovation, and a relentless drive to push the boundaries of our knowledge. The formation of Uranus is a mystery deeply tied to the broader evolution of the solar system. Current theories suggest that Uranus, like Neptune, formed in the colder outer regions of the protoplanetary disk, where ices could condense and coalesce into massive planetary cores. These cores, surrounded by lighter gases like hydrogen and helium, eventually became the ice giants we know today. But the exact sequence of events remains unclear. Why did Uranus and Neptune fail to grow as large as Jupiter and Saturn? Was their growth stunted by their position in the disk, or did interactions with other forming planets scatter them outward, halting their development? Further complicating the picture is Uranus's axial tilt. The prevailing hypothesis is that a collision with a massive body, possibly as large as Earth, knocked Uranus onto its side during its early history. Such an event would have had profound effects on the planet's development, influencing everything from its rotation and internal heat distribution to the formation of its moons and rings. Investigating the scars of this ancient impact, whether through the dynamics of its satellites or the structure of its interior, could provide critical insights into the chaotic processes that shaped the early solar system. Uranus is a planet of extremes, a place where the familiar rules of planetary science seem to bend and break. Its tilted axis, which causes the planet to spin almost on its side, results in a bizarre seasonal cycle. Each pole experiences decades of continuous sunlight followed by decades of darkness, a phenomenon that drastically affects its atmosphere and weather patterns. This tilt is thought to be the result of a massive collision billions of years ago, yet the precise details of this event remain shrouded in mystery. What kind of object could have struck Uranus with enough force to tip it over? And how did such an event shape the planet's evolution over time? The planet's atmosphere, though serene in appearance, hides dynamic processes. Methane gives Uranus its pale blue color by absorbing red light, but beneath this calm exterior lies a chaotic world of storms and winds that reach speeds of up to 900 kilometers per hour. These winds, combined with the planet's extremely low temperatures, the coldest in the solar system, create an atmospheric system that defies easy explanation. Unlike Neptune, Uranus emits almost no internal heat, leaving scientists puzzled about the source of its atmospheric energy. Could the lack of heat be another clue to its tumultuous past, perhaps tied to the same event that tilted the planet? The magnetic field of Uranus is equally perplexing. Unlike Earth's relatively symmetrical magnetic field, Uranus's is wildly tilted and offset from the planet's center. This creates an asymmetrical magnetosphere that twists and bends as the planet rotates, generating unique auroras and interactions with the solar wind. Understanding how this magnetic field is generated could provide insights into the planet's interior, where extreme pressures and temperatures might produce exotic materials like superionic water, a phase of water that conducts electricity like a metal. Uranus is encircled by a system of narrow, dark rings that are both fascinating and mysterious. Unlike the bright and icy rings of Saturn, Uranus's rings are composed of darker material, possibly rich in organic compounds. Their origin is unknown. They may have formed from the remnants of a shattered moon or a captured comet. Studying these rings could reveal not only the history of the Uranian system but also broader truths about the formation and evolution of planetary ring systems throughout the solar system. Beyond the rings, Uranus boasts a collection of 27 moons, each with its own story to tell. Titania and Oberon, the largest moons, show evidence of past geological activity, such as tectonic rifts and impact craters. Miranda, with its dramatic cliffs and varied terrain, appears to have been torn apart and reassembled, suggesting a violent history. Some of these moons might even harbor subsurface oceans beneath their icy crusts, warmed by tidal forces or residual heat. If confirmed, these oceans could provide habitats for microbial life, making Uranus's moons key targets in the search for life beyond Earth. Despite its many mysteries, Uranus remains one of the least studied planets in the solar system. Voyager 2's flyby in 1986 provided the only close-up data we have, and much of what we know about the planet is still based on this brief encounter. However, new technologies and growing interest in ice giants have placed Uranus at the forefront of planetary science. Future missions to Uranus could include orbiters and atmospheric probes designed to study its atmosphere, interior, magnetic field, rings, and moons in unprecedented detail. Such missions would not only answer long-standing questions about Uranus but also provide critical data for understanding similar planets in other star systems. The importance of Uranus extends far beyond the solar system. Many of the exoplanets discovered in recent years are similar in size and composition to Uranus and Neptune, yet we know relatively little about these types of worlds. By studying Uranus in detail, we gain a window into the conditions and processes that shape ice giants, helping us interpret the data from distant exoplanets and refine our models of planetary formation and evolution. Uranus is a world of contradictions. A cold planet with dynamic winds, a tilted giant with a lopsided magnetic field, and a serene-looking orb that hides a turbulent past. Its exploration represents not just the next step in our understanding of the solar system but also a journey into the unknown. The secrets of Uranus hold the potential to redefine what we know about planets, not only in our own neighborhood but across the galaxy. Each question we answer about Uranus brings us closer to understanding the fundamental processes that govern the cosmos, reminding us that even the quietest, most distant corners of our solar system are filled with wonder. The journey to uncover Uranus's secrets is a testament to humanity's insatiable curiosity and drive to explore the unknown. While Uranus orbits quietly on the fringes of the solar system, its unique properties and mysteries make it a dynamic laboratory for answering some of the most profound questions in planetary science and beyond. Studying Uranus isn't just about understanding one planet, it's about understanding the broader context of how planets form and evolve. Ice giants like Uranus represent a middle ground between rocky terrestrial planets and massive gas giants, offering a critical missing piece in the puzzle of planetary diversity. By examining Uranus, we can better understand why the planets in our solar system are so different from one another and why planets in other systems seem to exhibit such an incredible variety of sizes, compositions, and orbital configurations. For example, many exoplanets discovered in recent years fall into categories known as mini-Neptunes or super-Earths, which share similarities with Uranus and Neptune in terms of size and possible composition. These planets are among the most common types found in the galaxy, yet they remain poorly understood. Uranus, as an accessible ice giant within our solar system, provides an invaluable analog for studying these distant worlds. Understanding its atmospheric composition, internal structure, and magnetic field could provide the key to deciphering data from exoplanetary systems. One of the most exciting prospects in Uranian exploration lies in its moons. Among the 27 known satellites of Uranus, the 5 largest, Titania, Oberon, Umbriel, Ariel, and Miranda, are especially intriguing. These moons are geologically diverse, with surfaces marked by canyons, craters, and evidence of past tectonic activity. Some even show signs of cryovolcanism, where icy materials erupt instead of molten rock, reshaping their surfaces over time. Titania, the largest moon, is particularly interesting because it may harbor a subsurface ocean beneath its icy crust. If such an ocean exists, it could potentially support microbial life, shielded from harsh radiation and sustained by chemical energy from the moon's interior. Similarly, Ariel, with its relatively smooth surface and bright features, might hold clues to recent geological activity that could also indicate the presence of subsurface liquid water. Miranda, the smallest of the major moons, is perhaps the most visually striking. Its surface is a patchwork of immense cliffs, ridges, and unique formations that appear to be the result of multiple episodes of tectonic and cryovolcanic activity. The origin of Miranda's bizarre terrain remains a mystery, but its study could reveal much about the forces shaping icy moons across the solar system. Exploring these moons could provide critical insights into the potential for life on icy worlds. As scientists increasingly consider subsurface oceans as prime locations for habitability, Uranus's moons offer compelling targets for future missions. They may even rival Europa or Enceladus, moons of Jupiter and Saturn, as candidates for astrobiological studies. Sending a mission to Uranus presents significant engineering and technological challenges. Its vast distance from Earth means that a spacecraft must travel for 10 to 15 years to reach the planet, depending on the trajectory and available propulsion systems. Once there, the spacecraft would need to operate in extremely cold temperatures and communicate across billions of kilometers, with round-trip signals taking nearly 6 hours. Powering such a mission requires advanced systems like radioisotope thermoelectric generators, RTGs, which can generate electricity from the heat produced by radioactive decay. These generators have been successfully used in missions to deep space destinations such as Saturn and Pluto. Additionally, instruments designed to withstand the frigid environment of Uranus would need to be lightweight, robust, and capable of operating autonomously due to the time delay in communications. A future Uranus mission would likely consist of an orbiter and an atmospheric probe. The orbiter would conduct long-term studies of the planet, its moons, rings, and magnetic field, while the probe would descend into Uranus's atmosphere, directly sampling its composition and structure. Together, these components would provide an unprecedented level of detail about the planet and its system. The exploration of Uranus is not just about solving planetary mysteries. It's about pushing the boundaries of human knowledge. By studying this distant world, we gain a deeper understanding of the processes that govern the solar system, from planetary formation to magnetic field generation and the dynamics of icy environments. Uranus also serves as a stepping stone for future exploration of even more distant worlds. Lessons learned from a Uranus mission could inform future missions to Neptune and its largest moon, Triton, a world with an active surface and retrograde orbit that suggests it may be a captured Kuiper Belt object. Beyond Neptune, Uranus could serve as a gateway to understanding the vast, unexplored regions of the outer solar system, including the Kuiper Belt and Oort cloud. In the context of humanity's broader exploration goals, Uranus represents a vital frontier. As we develop the technologies and capabilities to study distant planets, we also prepare for the challenges of interstellar exploration. The knowledge gained from Uranus could one day guide us as we venture beyond the solar system, seeking to understand the countless planetary systems scattered across the galaxy. Uranus reminds us that even in the quietest and most distant corners of our solar system, there are stories waiting to be uncovered. Its tilted axis, icy moons, and dynamic atmosphere are just the surface of the mysteries it holds. Each step toward exploring Uranus brings us closer to understanding not only this enigmatic planet but also the processes that have shaped the universe itself. As humanity continues to look outward, Uranus stands as a beacon of possibility. Its exploration promises to deepen our knowledge of planetary science, inspire future generations of scientists and